we will get a brief review of what's going on in terms of ANOVA. The reason we have ANOVA, of course, is because when we use some other methods to test whether the mean of several small populations, whether they are equal to each other or not, when we use hypothesis tests, there is something that is undesirable. So the most important thing we have the example is, say we have 3 small populations, and we want to test whether their means are equal to each other or not. We mentioned this before. So in this case, if you want to test these 3 small populations, whether they have equal mean or not, you have to do 3 things, 3 hypothesis tests. First one, mu1 is equal to mu2 or not. You have to test it. The second one, mu2 and mu3. And then also you have to test mu1 and mu3. So in this case, you're going to find out. Of course, according to each hypothesis test, you can get a result, whether they are equal to each other or not. And suppose, in this case, they are all equal to each other. But for each hypothesis test, there is a significant level, alpha. Or, in other words, it is the confidence interval that's 1 minus alpha. And basically, this one means the probability that this will happen. And so let us say the alpha significant level is 0.05. And here it should be 0.95. Okay? So from each hypothesis test, you get a result. And the probability that this result will hold or this result is true is 0.95%. But in this case, we have to test 3, okay? For all these 3 tests to hold, for all of them to be true, it has to be 95% times 95% and times 95%. So that is 0.95% to 3's power, okay? So basically, in this case, if you want to test it, of course you can do that, but the significant level or the confidence interval, the probability that these hypotheses, H naught will be true, will be different. It's no longer 0.95%, it's 0.95 to 3's power, okay? So to overcome this kind of difficulty in our reasoning, that's the reason we have ANOVA. And through this kind of analysis, we have 3 hypotheses, okay? It has to hold assumptions. So the first assumption is, okay, those small populations must be a normal distribution, okay? They all have to be normally distributed. The second one, okay, is the variance of the first population must be equal to the variance of the second population and for the R's. This is what we call homogeneous variance. Homogeneous okay? So basically you have to have these 2 assumptions, okay? So as I mentioned before, in the final, if I'm going to make a question a little bit more complicated, what I can do is, okay, ask you to test this first, okay? Ask you to test this first. And then if it is true, of course, you can use ANOVA, right? If it is not true, you have to use hypothesis test, the traditional hypothesis test. You cannot use ANOVA if this is not true. Of course, in this case, from the traditional hypothesis test, you will compare mu1, mu2, mu2, mu3, mu1, mu3. From there, you know where the differences come from, because they may be different, right? And from here, you can tell where the differences come from. But from ANOVA, we are testing the whole things. We are looking at the whole sample. So in this case, we have to deal with where the differences come from. Okay, so there are several differences. The first one is the difference comes from factors. Okay, what means factors? So that means indeed they are different. So let us say there are R machines here. Okay, if each machine is different, of course the difference may come from because this machine is different from the other machines. Okay, so that is called the difference from the factors. The other one is called difference from error. Okay, as we know, even for the same machines, okay, the same machine, this machine will produce a lot of products, even though they come from the same machines, but the products themselves will be different. It is not because it is a different machine, it's because due to probability, okay, because each machine has certain kind of deviation, okay. When you get the machines out, okay, there may be something different there. It is hard to explain them because we know it is come from the same machine, but it is different, okay? So this is the other kind of difference, the sources of difference. And then we have, of course, if you add these two together, what you get a total difference, right? So let us put it here. Okay, so we get a sample out of it, okay? Get a sample out of the productions, okay? The products. And of course, we are looking at this individual item with the whole population, okay? So this is the mean for all of the products, okay? This is the mean for all of the products. So this is, we call deviation okay, total deviation, okay? And then, of course, we are looking at individual machine, right? If we look at individual machine, let us say this is from machine 1, okay? Machine 1, the quality of the products has a mean, right? We call the mean 1, okay? And since we put down Xij, right? So let us use I. So let us say we select this item randomly, okay, and we want to know what's the difference there. So the first thing is we can look at the whole thing. This is the mean of the whole population, and this one is the mean of that machine, okay, only one machine. And also we know this machine may be different from the whole population. This is the population mean, okay, for the whole population. And here we are looking at individual machine, okay, so this individual machine may be different from the whole population. So that means this machine is indeed different, okay. So here this is called deviation due to error. Right? Because we know this is from the same machine. If there's any difference there, we don't know why. Because it is indeed from the same machine. So if it is different, it is due to probability. Okay? And here, it is a single machine. The difference with a single machine and the whole population. So if there's any difference, we know indeed something wrong there. So that means each machine is different from the whole population. So this is what we call deviation due to factor, okay? And this is, let me put down the Chinese there. And this is Okay? So from here you can tell what's going on there. This is because the machines are different. This we don't know anything about it because it's just due to probability. And here it is the whole difference there. And as we say, in this case, it will be a little bit difficult here because you have to add the whole thing up. And because you have machines and also within each machine you have a lot of products there. Okay, so you have to deal with two things. One is machine and one is the products within the machine. And we say we have our machines, okay? We have our machines, and for each machine we have, okay? Because this is population, so we use capitalized letter, okay? We use N, okay? So for this case, okay, we have 1 to R. I denotes machine, okay? I denotes machine. J denotes the product within this machine. And this time we talk about it. So for the first machine, okay, we have X11. This means the first machine, and this means the first product. The first product of the first machine. So you have the first machine and you have the N1's product, okay? The second machine, okay, 2 denotes the second machine, and then the first product. The same thing here. And you have R machine, right? So X, R machine, the first product, and then R machine, and R's product, okay? And what's the total there? We say we have a total of N products, okay? We have N products. So N should be equal to summation I from 1 to R and J from 1 to Ni, and this is 1, right? Okay? So from here, what you get? Because this is from 1 to Ni, okay? So it means 1 is added Ni times. So what do you get? You get this. I is equal to 1 and R from 1 to R, and here you get Ni, right? And so from here, what do you get? You get N1 plus N2 plus Nr, okay? So the total number is N, okay? The total number is N. And for each machine, you have Ni, okay? For each machine, you have Ni. Of course, if we get all these, okay, it's still not enough because we want to analyze the whole thing, right? And so we have to find out how to get another way, okay? First, we need to have a statistic. So what kind of distribution we're going to use in dealing with all this? So first, we have to know where the difference comes from. The difference may come from the total, right? The difference may come from probability, okay? Is a random thing, and this is the difference come from the machines, okay? So let me get this. Okay, so you have Xij minus mu, okay, equals Xij minus mu I plus mu I minus mu. Okay? So from here, you know, this is the total difference, right? The total difference from the first one is a random, okay? This is random probability. And this one is because the machines are different, okay? You have two things. And then how to deal with it? So we square them, okay? We square them. So Xij minus mu square, okay? And then Xij minus mu I square, and plus mu I plus minus mu square, right? But for each case, you only add 1, right? But you want to add the whole thing, every product in this population, right? So you have to have two summations. Summation. This is from this is from the machines, okay? 1 to R, and this is J 1 to Ni. Okay? The same thing here. Okay, the same thing here. Okay. And somehow we can simplify it. Okay, we can simplify this thing, and what do we get? Actually, hold on, I make a mistake here. So because we make a square here, right? Okay, because we make a square here, so we have to have this one. Summation, right? And xij minus mu I plus mu I minus mu squared. Sorry about that. So, and of course, this time we already show it. What we end up with this. Xij minus mu I squared plus summation mu I minus mu squared, right? And so this is what we call SST, sum of square of total. And this is sum of square of error. And this is sum of square of factor, right? Okay, so in this case, we know what's going on here, okay? And last time, we discussed, what's going on in terms of all these numbers. And I think, first let me briefly tell you, most likely in each problem, you have to get a ANOVA table, okay? So when you work on the problem, actually the best thing is to get the whole thing here. The first one is the sources of deviation. The second one is SS. This is called sum of square. For sum of square, we have three. Sum of square total, sum of square error, and sum of square due to factor, okay? So this is the sources of error. If it is due to factors, it is listed here. And due to errors, and this is the total deviation, okay? So here it is sum of square, so you have to put in sum of square factor, right? And here you have to put in sum of square error. And here you put in sum of square total. And then you have to deal with degrees of freedom, okay? Degrees of freedom. As we know, we are testing our machines, right? We are testing our machines. And we want to know what's the degrees of freedom here. So the degrees of freedom is, and let me put down the formula in terms of sample. So this is the formula in terms of population, right? Let me put down the formula in terms of sample. So it should be summation I from 1 to R, J from 1 to Ni. Because it is simple, so we use little n, okay? And then Xij minus X bar G. Okay, X bar G is the mean of the whole sample. Okay, this is the mean for the whole sample. And then summation Xij minus X bar I, okay? Square, and plus summation X bar I minus X bar G square, right? Okay, so we are looking at the factors. Okay, we are looking at the factors. So there is a total of R machines. So there are machines here. Okay? So when you look at this, there are R machines, but there is one mean. Okay, this is sample mean for the whole sample, right? We know this. So then you have to subtract one of the degrees of freedom, because there are R machines, but there is a one mean of the total mean that is known. So the degrees of freedom has to minus 1. So the degrees of freedom is R minus 1. If you look at this one, right, we know the total is n. Okay, so because when we use population, we use big N, right? And when we use sample, we use little n. For this part, okay, the total numbers of sample is n, but you know mean, right? You know mean here. You know one mean here, so the degrees of freedom is n minus 1, right? And what is n? N is actually summation ni, okay, I from 1 to r. And this is actually n1 plus n2 plus nr, right? Okay, so here the degrees of freedom is summation ni minus 1, okay? Just as with the example we have, right? We say if for t, okay, for t distribution, if we have sample size, if the sample size is equal to n, for a t distribution, if the sample size is n, what's the degrees of freedom? N minus 1, right? So here is basically the same thing, okay? Basically the same thing. And here is the same thing too, right? It's like you have R machines, okay? And you know this one, right? So what's the degrees of freedom? R minus 1, okay? What about here? Here you are looking at each item, right? Each item is ni minus 1, right? But you are looking at R machines, right? So the first one, the degrees of freedom is n1 minus 1. What about the second one? It is n2 minus 2, right? And then what about the last one? It's nr, I'm sorry, it's still minus 1, right? Because the degrees of freedom. n1 minus 1 for the first machine. For the second machine, n2 minus 1, right? For the R's machine, it is nr minus 1. So what is the degrees of freedom? The degrees of freedom is n summation of ni minus r, okay? So this is summation ni minus r. Okay, and then you are going to deal with ms. So that's mean square. This is sum of square, and this will be mean square. So this one, okay, for each of the sum of square, if you want to get mean, you have to divide them by the degrees of freedom. So SSF, so MSF. So the first part, mean square due to factors, that would be SSF divided by R minus 1, okay? And for this one, it is MSE. It is equal to SSE divided by summation Ni minus R, right? And MST, it is equal to SST divided by summation Ni minus 1, okay? Okay, so that's probably what we ended up last time, okay? So we just done a brief review of what's going on last week. Any questions? So in terms of the reasoning, basically it's almost the same as before. But here in this case, we have a new distribution. It is F. So of course, from the sample, you can get MSF and MSE, right? And then from here, actually, you get MSF divided by MSE, okay? It is a F distribution, okay? It is an F distribution. And this F distribution, the degrees of freedom is R minus 1, okay? And then summation Ni minus R, okay? Okay, so basically, whenever you look at the questions, you need to have this table in mind, okay? Sum of square, degrees of freedom, mean square, and the factors due to errors, and the total here, okay? And then, of course, it gets to the last part. We have to have a hypothesis test, right? Still, we have to test it. So from the sample, you get mean square due to factors and mean square due to error. And from here, you get the observation, right? So you get a sample and you get a value here. If this value is greater than the critical value, then what would you do? You're going to say reject H naught. So what does that mean? That means the population mean, that means the machines, okay? For each of the machines, they are different, okay? They are different. Let me put down here. So let us say if F naught, this observation value, okay, this observation is less than this, then what you get? You're going to say we accept H naught. So that means the machines, okay, are basically the same. Of course, later on we're going to explain why we use F distribution and why we use right tail test. Okay, this is a right tail test. Okay, any questions? Let us take a break. The topics here. So when you do ANOVA, you have to be very careful. First one, you have to get the difference from the factors, okay? The difference from the error and difference from the total. And the formula is actually here. As you can tell, it's kind of complicated. SST, sum of square total, is the difference, okay, of each individual item with respect to the whole population mean, okay, the mean of the whole population. Of course, in this case, we are talking about a sample, right? The whole of the sample. So sum of square total you are dealing with this is the each individual item and the grand population mean, okay? And sum of square error, you are dealing with the item within each machine, okay? For sum of square error, because it's due to probability, due to random factors here. So you are looking within machines. So it is each individual item with each individual machine. So you are looking at the individual item within each machine, and this is the sample mean of each machine. And if you are looking at factors, you are looking at the machines and the whole sample, right? So this is the mean for each machine, okay? And with respect to the difference with respect to the whole sample, okay? This is the mean from the whole sample. So if you know the definition of deviation due to total, deviation due to error, and deviation due to factor. If you remember the definition, you should be able to get the result here. Okay, and then we talk about this. We say because basically if H naught is true, then you will expect mu1 is equal to mu2 is equal to mu r. And certainly x bar 1, okay, will be likely be equal to this. But first you have to remember, we are not dealing with the population, we are dealing with the sample. So when you take samples, there is sampling error, okay? There is a sampling error, so you won't necessarily get this. So if this is true, right, imply this should be true. And what you get? SST must be equal to SSE, because if H naught is true, then this one should be equal to 0, okay? But in this case, we are actually looking at the sample here, okay? So it won't necessarily be true. On the other hand, okay, because if you have more machines and you have more products, okay, for more machines and more products from each machine, then you know this will necessarily be larger, right? So you have to take into account the number of products and also the number of machines. So when you look at these statistics, you have to look at the average, okay, and the average is mean. So actually what you should look at is mean SF and mean SE. So now the next step, we are trying to figure out MSF and MSE. When it is true, okay, we are looking at the expectation, what it is going to be. Okay, so let me erase this. Expectation of MSE, okay? On average, what would you get if you have MSE? And MSE is expectation SSE divided by the degrees of freedom here, right? The degrees of freedom is summation Ni minus R, right? Okay, any questions? And what is that? Expectation of MSE. This is a constant, right? This is a constant, so we can move this out. So it is 1 over summation Ni minus R, expectation. Okay. SSE is the sum of square of the deviation due to error, right? So we are looking within each machine. So it is summation Xij, this individual item, and now we are looking at the difference within the machine. So this is minus X bar I squared, right? And this is I from 1 to R, J from 1 to Ni. Okay. So we have to get ourselves familiar with some of the formula. So remember, this class, okay, the test is cumulative. So when you have final, it's going to be tested from chapter 1 to the end, okay, what we talk about here. So you have to remember all the formula here. So SI squared, okay, we are dealing with this. And what is this? This is actually Ni minus 1, right? Summation, okay, Xij minus X bar I squared, right? And J is from 1 to Ni, right? In the past, okay, we have only one variable, right? So we are dealing with X squared. SS squared is equal to 1 over N minus 1 summation Xi minus X bar squared, right? And I 1 to N, okay? But this is when we are dealing with only one variable, right? And here we have I machines. We have R machines actually, okay? We have R machines, okay? So if you look at this part and this part, there is something familiar, right? There's something familiar. So actually you know SI squared times Ni minus 1, okay, is equal to summation J from 1 to Ni and Xij minus X bar I squared. Okay? Any questions so far? So from here, what would you get? Actually, you can get this part is equal to this part, right? Okay? Okay, so then let us get this. 1 over summation Ni minus R expectation, okay, summation I from 1 to R, and this is SI squared Ni minus 1. Okay? Any questions? And also from here, what would you know? We know expectation Sx squared is actually equal to sigma x squared, right? Okay? And this part is a constant. So actually this part is not affected by this expectation. This part, it will be affected by expectation, right? Okay? So then what would you get? You get summation ni minus r and summation, okay, sigma I squared ni minus 1. Okay, any questions? Because this is summation, right? I from 1 to r. So what do you get? You get 1 over summation ni minus r n1 minus 1 sigma 1 square, right? And then n2 minus 1 sigma 2 square and nr minus 1 sigma r square, right? Any questions so far? And when we do ANOVA, right, remember we have an assumption. What's the assumption? Homogeneous variance, right? So sigma 1 square is equal to sigma 2 square is equal to sigma r square is equal to sigma square, right? So actually this one will be sigma square, this one will be sigma square, and this one also will be sigma square. How many do we have? We have 1 over summation ni minus r times, okay, because this is from n1, n2 to nr, right? So you have summation ni minus r and times sigma square, and that is equal to sigma square. So in this case, we prove the expectation of MSE is actually equal to sigma square. Okay, from here we know expectation of MSE is actually equal to sigma square. Any questions? Okay, then we're going to do the next one. The next one is expectation of MSF. Can I erase it? So give you 2 more minutes. So this is the expectation of MSE. We find out that it is equal to sigma square. And the next one we're going to deal with MSF. Of MSF. Expectation of MSF is equal to expectation of SSF divided by what should be here? Because we are dealing with factor, right? So that's machines. The difference for the machines with respect to the whole sample, right? So we have R machines, so it should be R minus 1, right? Okay? And what's the next step? The next step is we have to know what is MSF, right? So it is equal to 1 over R minus 1. And this one is summation, because we are looking at the differences of the machines. X bar I minus X bar G square, right? Okay? So this will be a little bit more complicated. So let us just try to be patient here. Okay. So what do we get? 1 over R minus 1 expectation, okay, summation, x bar square minus 2x bar I x bar g plus x bar g square. Okay? We just expanded, right? We just expanded. A minus b square is a square minus 2ab plus b square. Okay? And then how to deal with it? So this is from I from 1 to R, J from 1 to Ni, right? Sorry, it should be xi squared, right? Okay, it should be there. Okay, then let us try to expand it again. Expectation, okay? Summation x bar I squared minus, this one is I, right? This one is J. And this one is x bar G. So as you can tell, actually x bar G is not affected by J, right? This is a constant. So we can move that thing out. But anyway, let us take it step by step. Summation, so 2 summation x bar I, x bar G, plus summation x bar G squared. Okay? And this is I from 1 to R, J from 1 to Ni. The same thing here, 1 to R, 1 to Ni, 1 to R, and 1 to Ni. Okay. Okay, so what do you get here? In this case, this I, because the first step, the first summation, if you want to add, you add from J, right, and 1 to Ni. So how many x bar I squared here? For each one, right, for each machine, you produce Ni products, right? And so in each case, you add x bar I squared Ni times, right? So what do you get? Summation I equals 1 from 1 to R, Ni x bar I squared, right? Because you want to get rid of this. And how many times do you add? You add from 1 to Ni, okay? So let me do this. J from 1 to Ni and x bar I squared, right? Because first one, x bar I squared, right? The second one, also x bar I squared, right? How many times you have Ni times, right? Because here. So this one should be equal to this one. Okay? Any more questions? And then let us talk about this one. The same thing, right? Because this is x bar G squared, so that means it is not affected by J, neither is it affected by I, right? And we say summation I from 1 to R, J from 1 to Ni. What is this thing equal to? It's equal to N, right? So what do you get? You get N x bar G squared. Okay? Okay, so I will erase this. So this part shows this one is equal to this part here. Okay? Okay, the difficult part is here. Okay, the difficult part is here. Okay, so we can move x bar G out, right? We can move x bar G out. So this is equal to x bar G, okay, summation and summation. Because this, we say this part is equal to Ni x bar I squared, right? So then, if we move this out, okay, we already moved it out, and so this part is actually the same as this part, except it is square, it is not, right? So what does this mean? This means that this is I from 1 to R, ni x bar I, right? Basically, we already agree this part is equal to this part, right? And this part is basically the same thing here. The difference is it is square. It is not, right? So in this case, we can say this one should be true. Okay, this one should be true. Okay, then what is this one? Let us try here. X bar I is equal to 1 over ni summation xij, j from 1 to ni, right? Okay? We are looking at individual machines. Before we discuss this kind of problem with several variables, we only have x bar is equal to 1 over n summation xi, right? So this is the original formula. But now we are dealing with several different machines. Okay, we have several small populations, several small samples. So in this case, we have to deal with x bar I. That's the mean, the sample mean of each machine. Okay, and it is divided by ni. That's the number of samples you have, and this one is xij, right? J from 1 to ni. Okay. Any questions? Okay, then from here you know x bar I is equal to, times ni is equal to summation j from 1 to ni xij, right? Okay, so actually this part is what you see here, right? This part is actually equal to this part, right? Okay? And so, if you look at this whole thing, what is this whole thing equal to? Because in this case, we are only looking at the ice machine, right? We are only looking at one machine at a time. And this one is the ice machine, right? And how many machines we are looking at in this case? Because from this part, we are only looking at one machine, right? But actually, because of this summation, how many machines we are looking at? Actually, we are looking at all of the machines because it is from 1 to R, right? Okay, from 1 to R. And so if we get a summation here, that is I from 1 to R, so then we have also to add from I is from 1 to R, right? So what do you get? You get summation, okay, xij. Okay, from here you know you are dealing with every sample, right? You are dealing with every sample. And so this one is actually equal to n times x bar g, because x bar g is equal to 1 over n summation xij, right? So because of this we know, okay, because of this we know this one is actually equal to n times x bar g, okay? This one is actually equal to n times x bar g. You want to be careful because the formula is getting more complicated, so you have to remember each step, how you get to the next step, okay? So basically, we already know this part is equal to n times x bar g squared, right? And this part should be equal to 2 times x bar g times n times x bar g, right? So then the whole thing should be equal to r over 1 over r minus 1 expectation summation I 1 to r ni xi bar square minus 2n x bar g square plus n x bar g square. Okay? So this is what we get. So then we can simplify further. Actually, what do we get? We get 1 over r minus 1 expectation summation ni x bar I square, I from 1 to r, minus n x bar g square. Okay? Any questions so far? So it is a little bit complicated. You have to get step by step, okay? Compare the formula and compare which part, okay? Say these are, you are looking at this part, you have to get it from here to here, okay? Remember how you get those things there. Any questions? Okay, then there's something we know, right? There's something we know here, okay? But before we do that, let us simplify it further. Okay, anyway, we can deal with it here. Okay, so if you know x and the mean is mu x, the variance is sigma x squared, right? If you know that, then what about x bar? X bar would be mu x, and this one is sigma x squared divided by n, right? Okay? Okay. But what about here? Because we have expectation move inside, right? This part has to be we have to do expectation here. And so actually you are looking at expectation x bar square, right? Okay? Can anyone tell me what is expectation of x squared? What is this equal to? Expectation x squared. It will be in the final, okay? So what is this equal to? It is equal to 2 parts. The first part is mu x squared, right? The second part is vx, okay? But here you are looking at this one, right? So it is mu x bar squared plus vx bar, right? And mu x bar is actually equal to mu x, right? X is here and x bar is here. The mean is the same, right? The mean is the same. But this one, of course, is different. Okay, so what is the next step? So you have to remember all these formulas. So let us continue. Let us stop here. You have to do teaching evaluation.